Uh, in this video, we're going to talk about tangent planes. So this topic is actually an extension of section 14.3, which discussed partial derivatives. The reason that the topics are separated like this is because I'm actually mostly following a textbook that's different from the one that's assigned to our course. So the topics are organized slightly differently. However, what's being discussed is essentially the same. Okay, so let's talk about tangent planes. If you remember back in Calc 1, the derivative tells us the slope of the tangent line. So we can visualize it here, where we have the function f of x in purple, and if you calculate the derivative at the specified point A, that tells you the slope of this tangent line in blue. So what we want to do for functions of two variables is to construct a similar object, which will now be a tangent plane to the surface that represents the graph of the function. To be able to construct the tangent plane, we'll need to use both the partial derivative with respect to x and also the partial derivative with respect to y. So the idea is going to be the following, right? So if you remember, the partial derivative with respect to x tells you the slope of the tangent line in the x direction, right? So you see how this purple arrow is parallel to the x-axis. And then similarly, the partial derivative with respect to y tells you the slope in the y direction. So again, this pink arrow is parallel to the y-axis. Okay, so to be able to construct the tangent plane, we need to know the normal vector to the plane, right? So here, in pink we have the tangent vector in the x direction, which can be constructed using the partial derivative. And we also have the tangent vector in the y direction, which can be constructed using the partial derivative. And these two vectors are part of the tangent plane. And because these two vectors are part of the tangent plane, their cross product will be orthogonal, producing the normal vector. So that's the basic idea. So I describe it here, right? So this vector here is a tangent vector in the x direction, so that's representing this pink vector here. And then this vector involving the partial derivative with respect to y is a tangent vector in the y direction. And as I said, if you calculate the cross product between these two vectors, it produces a normal vector to the tangent plane. So you can check this calculation, but performing this cross product will result in this normal vector written here. Okay, so we have the normal vector to the tangent plane. So one other thing we need to do to write down the equation of the plane is a point that lies on the plane. And so what we can do is just to take the specific point where the plane touches the graph of the function. And that's exactly the point described here, right? So the x and y coordinates are the given point A and B, and then the z coordinate is just the function value at this point. So plugging all this information into the equation of a tangent plane, into the equation of a plane, you obtain this expression here, right? So the normal vector A, B, and C is given by these coordinates involving the partials with respect to x and y, and then the x and y and z coordinates of the point is exactly these coordinates here. Okay, so we get this expression, and then we rewrite this expression in terms of z, and so we can write down the tangent plane in exactly this form here. Right, so notice that for the tangent plane, the coefficient of x is the partial derivative with respect to x, and the coefficient with respect to y is the partial derivative with respect to y. Okay, so that's how we can construct the tangent plane equation at the point AB.